So we've got a 5 kilogram box on a horizontal surface. Uh, so no box on a ramp yet. Right? The coefficient of friction between the box and the surface is given, and a horizontal force is pulling the box at a constant velocity for 10 centimeters. Right. And we want to talk about this not in terms of forces and accelerations necessarily, but we want to talk about it in terms of energy. So we have a box. It's being pulled along horizontally. There's some kinetic friction slowing it down. And it's got its weight going on here. Did I leave out any forces? Jaden says N. Yes. If we are resting on a surface, there is for sure going to be some normal force. For simplicity, let's define our coordinates. Say positive x is to the right, positive y is up. And we don't really have any vectors to break down, so let's just list off our forces in vector form. So our normal force is nothing in the x direction, all in the y. Our weight is nothing in the x direction, all in the negative y direction. The pulling force is all in the x direction. Our friction is all in the negative x direction. And lastly, we have our displacement. Because we actually managed to tug the box to the right 10 centimeters. Okay. And we're told that our velocity that our velocity for the whole time is a constant, and that therefore our acceleration is 0. Okay. So that's everything broken down. Of the 4 forces that we have acting on the box here, 2 of them will do no work at all in this situation. So, Matthew, can you tell me which one of the forces that isn't going to do any work? Gravity. Yep. Gravity will do no work. Other Matthew. Matthew, can you tell me another force that is going to do no work? Normal force. Awesome. That is correct. So normal force and weight, they are only acting in the y direction, and our displacement is only in the x direction. So they will do no work. What about the work by the net force? Like, what's the net work being done on this box? So we're skipping from, we're going to part C here. So what's the net work done on this box? Uh, Zachary, what do you think? No? Nothing? Okay. Trainmaster. Yeah, it's 0. We're told that the box is being pulled at a constant velocity. Constant velocity means 0 acceleration. 0 acceleration means 0 net force. And if there's 0 net force, there's no work. So net force, no net force means no work. So all right. So let's get down to the pulling force and the frictional force then. So how much work is done by just the pulling force? Right, so here we've got a really simple, like we've got a constant force, right? It's a force of constant magnitude. So instead of representing work with an integral, we actually have a simplified version. Right? So force doesn't depend on s, right? We can factor force out of the integral, and then the integral of ds is just s. So if we have a constant force, then the work done is just F dot S. So the applied force is doing an amount of work equal to which is equal to what? Anybody? Let's do a little side calculation. Right. Sum of forces in the y direction is 0, which implies the normal force is equal to the weight. And that implies that the frictional force is equal to mu mg. Sum of forces in the x direction also 0, which implies that the friction equals the pulling force. Therefore, the pulling force also equals mu mg. So when we do P dot S, our force is mu mg. The distance that we have moved the box is S, and those numbers are given to us. So the coefficient of friction is 1/2. The mass is 5 kilograms. Gravity is about 10. And the distance that we've moved is about 1/10. Right? So this ends up being 2.5 joules. Does anyone have a question on this problem so far, on parts A or C? So having said that, having the pulling force does 2.5 joules of work, like adds 2.5 joules of energy to the box. So how much work must have been done by the frictional force, right? Which is part B of this question. Right, let's have someone venture a guess that hasn't talked today. So a Diawara or a Calderon or Zahn. Tell me what you think. Right, 2.5 joules of work done by the pulling force. That is 2.5 joules of energy added to the box by the pulling force. So how much work must have been done by the frictional force? Josue, it's okay to say I don't know. Just let me know that you're paying attention. Okay, totally honest. I appreciate that. What about you, Zachary? Again, totally okay to say I don't know. Okay. So we could do the same calculation for the frictional force. We could say, the work done is equal to mu mg times s, right? But we already know that there's no net work done on the box, right? When we did part C, we calculated that no net force means no net work. So if our pulling force did a positive 2.5 joules of work, then the frictional force must have been negative 2.5 joules worth of work. Right? Because that's how we get to an overall zero work. Right? So if we added energy to the box via our pulling force, the frictional force subtracted off that same amount of energy. All right. Any questions about this problem before we pull out a new one? Okay. Let's do another we'll do a relatively simple one. So let's say we've got a spring and it takes 500 joules of work to compress a spring by 10 centimeters. What's the spring constant, or what's the force constant of the spring? Well, so if we draw a picture, we've got a spring that prefers to be yay long, but we have squished it until it is yay long. And the difference between those two lengths is 10 centimeters. Okay, and this is going to be our delta x. So this is a one-dimensional problem, but we'll note that maybe that this is the positive x direction, like the direction in which the spring gets longer. And we'll pull out our definition of spring potential energy. So the potential energy stored in a spring is equal to the work that you had to do on the spring in order to stretch it, which is equal to 1/2 k delta x squared. So we'll do a little bit of algebra. We are given that this actually took 500 joules of work to compress the spring, which means it's also storing 500 joules of work in its compression. And if we let go, right, it would bounce back. So 500 joules stored there. We can solve for K. So K equals 2 times 500 over delta x squared, right? The change in x is 10 centimeters. So 0.1 squared. So this is 1,000 over, what, 0.1 squared is 0.01. So we're looking at 100,000. That is a pretty stiff spring, but it's not like super out of the ordinary. So the larger the force constant for the spring, the stiffer it is. So, for example, the shocks in your car, they're going to have a force constant, somewhere in the several 100,000 range. Whereas the springs that you might see in a university lab setting are more like 15. And if you've got a slinky that you play with at home, the spring constant there is probably more like 5. So there's a huge range of constants that springs can have, all the way from like 1 to 1,000,000. All right. Any questions on this calculation here? Okay. All right. Let's look at question 58. Things rolling downhill are another pretty common thing that we will run into, because we already love boxes on ramps, and things going down hills is just a natural extension of boxes on ramps. Let's take a moment and draw this out. So we're at the top of a hill, right up here. And it's a relatively gentle hill. (10 degrees). And the length down the hill is 100 meters. So we're assuming that the friction is negligible. So maybe this is actually a snow-covered hill and we're sledding down it or something like that. But if we're not going to consider friction, what is the speed of the wagon when it reaches the bottom? Well, there's a couple ways we could go about this. If we really wanted to, we could brute force it with Newton's second laws. We could do a force diagram for a box on a hill. And we could realize that part of the weight of the box is pulling it down the hill, part of it is pushing it into the hill. We could solve for an acceleration down the hill, and then we could use our kinematics to solve for the speed at the end of the hill. But that seems like a lot of work, and also we're in a chapter about energy, not kinematics. So instead, let us label the top of the hill situation A and the bottom of the hill situation B. So if we are neglecting friction for this problem, then that means that there are no external forces from A to B. I can spell external. Which means that there's no work done, which means there's no change in energy from A to B. Which means that the energy, the total energy at point A is equal to the total energy at point B. Now, we don't know about that many different kinds of forces yet. We know about some gravitational potential force. We know about, or sorry, we don't know about that many kinds of energy yet. We know about gravitational potential energy, MGH. We know about kinetic energy. And just today, we learned about spring energy. So, question, at point A, at the top of the hill, what kinds of energy does the box possess? I'm not looking for a number, I'm just looking for you to tell me what kind of energy. So at the top of the hill, Trainmaster, it has kinetic? So for it to have kinetic energy, it needs to have a speed. At the bottom of the hill, it's definitely going to have a speed. So for EB, we're definitely going to have kinetic energy. So 1/2 m velocity at b squared. And actually, that's what we're looking for. We're looking for velocity at b. So it's good thing that it showed up in our analysis. And then, yeah, you're right. At the top of the hill, it's going to have gravitational potential energy. It's going to have some height above the ground. Right? So at point A, it has height, and there's an energy associated with height. At point B, it has speed, and there's an energy associated with speed. No external forces means that these two quantities have to be the same. So our m's cancel out, And we can do a couple of steps of algebra to solve for our velocity at b. So vb is going to equal the square root of 2gha. So the only thing left to do is just calculate what is this height at a. Right? But the problem was kind enough to give us both the length of the hypotenuse of this triangular hill and also the angle of elevation of the hill. So our height at A is going to be 100 sine 10. Anyone have any questions on this so far? I actually want to redo this same problem, but I want to put friction back in. So let's do a quick force analysis. And let's say that the coefficient of friction between the cart and the hill, it's low, but not 0. It's going to be 0.1. So we will have a normal force, we will have the weight, and we will have a frictional force. And it'll be convenient to say that positive x is down the hill and that positive y is in the direction of the normal force. So now we can sum up the forces in the y direction. We have normal force, we have mg cosine 10. So the amount of normal force is equal to mg cosine 10. And that tells us the magnitude of the friction, which is what we were after for this little bit. So now that we know that there's some friction, we don't have no external forces now. Now we have friction. Friction is moving energy from our cart out of the system. So that makes it an external force. So we have now the integral of f dot ds equals the change in energy from A to B. The friction is a constant force along this length, right? So it's as you go down the ramp, the amount of normal force doesn't change, therefore the amount of friction doesn't change. So this integral gets simplified, and it can just be f times the change in s, right? And it's actually 100 meters down the hill that we've gone. So we're going to have mu mg cosine 10 times 100. And on the other side of the equation, we're going to have the change in energy, so the energy at B minus the energy at A, which is equal to 1/2 mv squared plus mg 100 sine 10. All right. For the calculation in the pink over here, have I lost anybody? Is everyone trundling along with us, or do I need to take a step back for a moment? Okay. Got a couple of pretty goods. Okay. So like we had in the blue, we realized there's an m in every term. So we have m's cancel out, and we can solve for v. So now instead of just having a 2gh in the numerator, we're going to have a 2. Oh, you know what? I forgot a negative sign here, because the friction and the displacement are going in opposite directions. So we have 2 times g 100 sine 10 minus mu g cosine 10. And then all of that square rooted. Okay. So when we include friction, we only get a speed of about 13 meters a second. So does everyone remember the roller coaster problem that we did on Monday? So if we wanted to add friction into our consideration of the roller coaster, we would actually need to know the exact length of track and its orientation at every moment. So that's why we ignored friction on Monday, because roller coaster track isn't flat, and so the amount of friction that the cart experiences varies from moment to moment, and so it gets messy. But just because it's messy doesn't mean you can't do it, right? So you've all had calculus, you've all had some geometry and some trigonometry, so it certainly would be possible to calculate the effect of friction on that roller coaster in loop-de-loop, yeah? Even if you'd rather not do it. Okay, so are there any final questions or comments for today? This is all that I had planned to present today. If you want to see the solution for the quiz question, you can stick around. But if you don't care to see that, then you can head out, and I will see you all on Monday. I wish you all a great rest of your week.